If I could travel at the speed of light, and I wanted to travel to our nearest celestial neighbour, the moon, I could make that journey in just 3 seconds. That's because the moon is a distance of 3 light seconds away from Earth. If I wanted to travel to our nearest star, the sun, and I could travel at the speed of light, and I wanted to have a very hot ending, I could travel from the Earth to the sun in a time of 8 minutes. The sun is 8 light minutes away from the Earth. If something happened to the sun, we wouldn't know about it. Nobody on Earth would know about it for at least 8 minutes from now. 8 minutes after it happened. Going a bit further afield now, if we think about some of the outermost planets in our solar system and think specifically about Neptune, Neptune is a few light hours away from Earth. And so if something happened to Neptune, if it blew up or if it turned purple, no one on Earth would know anything about that until around the time that many of us in this lecture theatre are tucking into our supper this evening. Going further afield still, to the nearest star outside of our solar system, we need to look into the southern sky and look towards a star shown in this arrow here in the bottom left corner, Proxima Centauri. Anyone who's been to the southern hemisphere and looked up at the night sky will recognize a number of stars in this image. The 2 brightest ones on the left are Alpha and Beta Centauri. The 4 on the right are the Southern Cross. And by thinking about lines constructed from the geometric shape defined by these 6 stars, you can pick out the south pole about which the sky seems to rotate, viewed from the perspective on Earth. But back to Proxima Centauri, I don't know if you can see it here, I'll zoom in just a little bit more. It's a remarkably ordinary, rather faint star in this image. Proxima Centauri is a mere 4 light years away from Earth. So we are observing Proxima Centauri here in 2019 as it was in 2015. So correspondingly, if it's 4 light years from our solar system, and if we see it in 2019 as it was in 2015, it is fascinating to ask the question, what would be seen by an observer on a planet orbiting Proxima Centauri now? The answer to that question is that they would see the President of the United States as Barack Obama, and obviously, if they had sufficiently sophisticated technology, they might even pick up on the fact that parts of the British media seem to fixate on the manner in which a British politician devoured a bacon sandwich. So we're looking back in time by 4 years, in the case of the nearest star outside of our solar system. Now let's move further afield still to our nearest cluster of galaxies outside of our own local group of galaxies. This cluster of galaxies is called Fornax. It is 100 million light years from where we are. And so we see it as it was 1 million centuries ago. The information about what Fornax was doing 100 million years ago is still encoded in the light that left Fornax 100 million years ago and has since been travelling towards us here on Earth. That information is frozen in time. From all of these galaxies here, if there were an observer with appropriately sophisticated technology sitting on a planet in orbiting on a star in one of these beautiful galaxies that together comprise the Fornax cluster of galaxies, what would they see looking back on Earth? Well, I think they would see dinosaurs stomping around, making dinosaur noises and eating each other. But enough of that particular bit of speculation. I'd like to underline an important equation in the business of cosmic history. When we look at distant objects in the universe, we are looking back in time. We are seeing objects as they were when the light left them, not as they are now, for that light has yet to land here on Earth. And this arises because light travels at a finite speed, as we discussed in Lecture 1. So when we observe some of the most distant objects in the universe, because the light travel time is so great, getting on for billions of years, never mind 4 years or 1 million centuries, but 1 billion years, that light travel time becomes comparable with the age of the universe itself. It's really crucial to hang on to the fact that for the most distant galaxies, light left them when the universe was a small fraction of its current age, which is nearly 14 billion years. This is a real benefit, by the way. It means we can claim that we are historians, and that can be an asset. But it does also underline the challenge involved in doing cosmology. I'm going to read you something rather poetic by Georges Lemaître, the famous Belgian cosmologist. The evolution of the world, here really meaning the universe, the evolution of the entire world can be compared to a display of fireworks that has just ended. Some few red wisps, ashes and smoke. Standing on a well-chilled cinder, that's this rocky planet of Earth, by the way, we see the slow fading of the suns, and we try to recall the vanished brilliance of the origin of the worlds. And I think that rather poetic description captures the business of what we're trying to do. From our place in space on this rocky planet, we're trying to look back and interpret things that happened in the distant past. We're doing so from our solar system, which, as you know, comprises a rather normal star, 8 planets these days, abundant dwarf planets, asteroids, and so on and so forth. All of that stuff that is in orbit around the sun has less than 1,000th in total of the mass of the sun. So how on earth, from the vantage point of this rocky planet, can we hope to make concrete advances in our understanding of what the universe is like and what the universe was like? It would be easy to be daunted by this, but it's important to hang on to the fact that basic observations matter, and wondering about the simple questions can sometimes be very revealing and reveal some important fundamentals. I want to begin with a concept known as Olbers Paradox. This is named after Heinrich Wilhelm Olbers and dates back to 1823. Olbers was not unique to reflect on what I'm about to describe. Others, such as Kepler, who was famous for thinking about how planets orbit around other stars and themselves, Lord Kelvin and others pondered this. Olbers' paradox went as follows: how come nighttime is dark? Because suppose we live in a universe that is infinite, that is homogeneous, and that is static and unchanging. And suppose that stars are switched on forever and never grow dim. A prediction of this, if every line of sight looking out from the Earth should sooner or later end up on a star, and the further out you go, the more such stars you would see, you predict from those very simple assumptions that the sky ought to be bright at night, as you integrate up the effect of going further and further out into space, gathering up all that light from the stars, assuming that once that light is launched, it propagates unimpeded here to Earth. But we all know, don't we, barring street lamps, the sky is dark at night. What gives? Well, we think that the universe is finitely old. We think that the speed of light is finite, as explored in my previous lecture. And we also think that only finitely many stars can be observed from Earth. This latter point arises because we believe, as I'll present later in the lecture, that the universe is expanding. And so light has an even harder job to get from distant celestial objects to us here on Earth. In addition to Olbers pondering this, Edgar Allan Poe also considered the same marvel. And he put it thusly: were the succession of stars endless, then the background of the sky would present a uniform luminosity, a uniform brightness. Since there should be absolutely no point in all that background on which there would not exist a star, unless, supposing the distance of the invisible background is so immense that no ray from it has yet been able to reach us at all. Edgar Allan Poe was not a scientist, but he was a creative who was free to think and figure out some important realities that are relevant to the discussion of cosmic history. This is from his essay entitled Eureka in 1848. Before we return to the difficult business of exploring the cosmos, I would like to make some general remarks about research in science in general. I'd like to underline, as I'm sure many here know, that actually we don't talk about scientific proof. The term proof is a term that belongs to formal mathematics, but in empirical science, our currency is evidence. Evidence gleaned from theory, from empirical measurement, and from observation. Our conclusions, our understanding, is forever provisional. If it is real science, it is testable, and therefore it is falsifiable. So we are all the time in the business of doing science and trying to understand more about science both on this planet and outside of this planet. What we do is we gather evidence and we try and interpret it in the light of the laws of physics as we understand them. So far, so good. But what's different about doing research in cosmology? Well, for a start, whereas in the lab you can run a different experiment with a bunch of lasers or a bunch of superconductors or a bunch of magnets, we have only got one universe. The clue is in the name. So we can't do statistics on an ensemble of 20 universes or 100 universes. Specifically, we cannot design and run experiments. We cannot rerun the birth of the universe as a function of magnetic field or as a function of temperature. All we can do is make observations which are themselves looking further and further back in time, looking at that information which is frozen in time. We are further hindered by the fact that for the first part of the universe's history, it was opaque to light. For the last part, the last 13 billion years or so, or a little more than that, we have actually been able, the universe is transparent to light. But for the first few 100,000 years of light, the universe is opaque to electromagnetic radiation to light. And that really does make things hard. More of that a little later. But I would like to mention it does mean that the physics of the very early universe is unknown, hard to discern, it is possible, it is unknowable, some of it. Some of it we can piece together on the basis of theory, and we can hope to verify on the basis of observations these days coming from gravitational radiation, not merely electromagnetic radiation. But let's press on, more on the nature of research in cosmology. I've been alluding to the fact that some of the relevant timescales here are 1 million centuries or 1 billion years. These timescales are not well matched to humans, of course. Individually, we may hope, please God, to live for 100 years. But even sentient, scientifically trained humans, even then, the timescale we're talking about is only centuries plural. The distances are pretty hard to determine. There are ways of doing that, but they're certainly huge. And that means the information we get is frozen in time from launched, emitted at a time when the universe was much younger. It is unavoidable that we have to extrapolate physics over very large ranges in space and in time. And specifically, we find that laws which are very, very well tested on the size scale of our planet and on the size scale of our solar system, I'm talking here about Newton's laws, they are really well tested on those size scales. If you go up in size by, say, 7 orders of magnitude, you get to the size of our galaxy, the Milky Way. And even by that stage, you find that the laws don't work. It's possible, of course, and we have the humility, of course, to say, maybe we should question those laws. That is a valid thing to do. But the preponderance of evidence at present is that we need to invoke something called dark matter and something else called dark energy. I won't go into details on these concepts and the evidence for them in this talk, but Gresham's visiting professor of cosmology will be addressing precisely these points on the 4th of November. But I'd like to understand that cosmic evolution and astrophysics and the geometry of space-time itself make this a bit of a tricky business. I'm trying to elicit your sympathy here. Cosmology is quite hard. And we have to make presumptions. We presume that the bit of the universe that we can observe is representative of the universe as a whole. We're making a really big, often implicit assumption that the laws of physics which have controlled the evolution of the universe to date are deducible. It's an amazing thing that thus far the laws of physics are intelligible. Albert Einstein himself marvelled at just this point. And so, having given you a bit of a context for the basis of cosmology, let me just indicate some of the get-outs for why Olbers Paradox isn't a paradox anymore. The universe is expanding. I'll be discussing that a little more later in my lecture. Light from more distant objects is stretched out. It's certainly possible the geometry of the universe may not be what we think it is. It's certainly the case, we think these days, it is widely accepted in the astrophysics and cosmology community worldwide that the universe is not temporally infinite, or indeed spatially infinite. It is absolutely the case, and we can verify this to some extent, that stars do not live forever. They are not eternal. They do not have infinite lifetimes. That being the case, we can begin to understand why we might not just be collecting on Earth all lights, all sources of light from an infinite number of stars in a static universe. It's because those assumptions that went into the first consideration of that paradox do not in fact hold. A lot of what I've just said can be encapsulated in the Copernican principle. This is sometimes called the cosmological principle. It takes its name from Nicolaus Copernicus, and it's really expressed in the following sentence. The universe is the same, whoever you are and wherever you are. This galaxy is much like the Andromeda galaxy, is much like the next galaxy along. There's nothing special about our vantage point, even if obviously, present company accepted, some of us like to think of ourselves as special. Certainly as a race, we're pretty special, but our vantage point, I think, we presume it is not. There is no basis for saying anything else. Of course, it's true that the Copernican principle is not exact. Sitting in a lecture theatre is not the same as sitting on the beach. Sitting in the interior of a star, not recommended by the way, is not the same as sitting in the cold environment of the interstellar regions in between stars. The Copernican principle holds better as you go to larger and larger scales. And by large here, I mean the scale of 1 million or so galaxies. That's when it starts to become a very useful tool in the toolkit for describing the universe. We may think of our planet as pretty special. There is a sense in which it is, absolutely. But really, we don't want to think about planet scales or solar system scales. We want to think about the individual entities or marker particles in cosmology as being units of galaxy. We cannot be parochial when we do cosmology. A galaxy is a marker in space, and the way galaxies move, as we observe them here on Earth, tells us rather a lot about how space-time itself is behaving. It's important to realise that galaxies are, of course, a three-dimensional distribution as we think about space. And this is a flyby reconstructed from some data called the Hubble Deep Field from the Hubble Space Telescope, hence the name. And you can get a sense of these lumps of matter in space, which are galaxies. So a galaxy is a conglomerate of something like 100,000 million stars. Those stars are gravitationally bound towards one another. It's not completely true to say they're freely floating in space, but let's hold on to that assumption for the next few minutes. Now, it turns out it's actually quite easy to measure the speed at which a galaxy is moving away from us. Some in this room may have heard of something called the Doppler effect. And if you've ever listened to the note of an ambulance siren as it comes towards you and as it recedes away from you, you'll notice there's a change in pitch. As the siren on the ambulance moving towards you is approaching you, the pitch is higher. As it's receding from you, the pitch is lower, as the wavelength of the sound increases. Of course, you only get to hear the pitch going lower if you're not standing in the path of the ambulance, but you're a bit set back on the pavement. This principle absolutely applies to light waves as it does to sound waves. So if we consider that we've got a source of waves, any kind of waves, but let's start to think about light. If your source of light is stationary and you've got an observer either on the right-hand side of the board or on the left-hand side of the board, you will receive those wavelengths of light exactly as they are emitted. But if your source of light is moving, let's say, if your source of light is moving towards you and you're an observer on the right-hand side of the screen, you'll see those wavefronts bunched up. The wavelengths will be shorter. Correspondingly, if you've got an observer on the left-hand side, the light that does arrive on the left-hand side will be stretched out. The wavelength will be longer. So, thinking about light, I now want to introduce the fact that particular elements, particular types of atom in the periodic table emit very specific colours or wavelengths of light. Many of you will be familiar with the orange street lamps that adorn our streets and give that familiar orange glow to the night sky on a cloudy night. This is because of the ionized sodium gas that's in the street lamp. If you measure a spectrum of that light, you will see there are very characteristic emission lines or peaks of light that correspond precisely to the fact that you've got sodium gas in your street lamp, which in turn corresponds to the fact that you've got electrons in the sodium atoms doing very specific transitions that give you that specific orange colour. Now let's do a Gedanken experiment. Let's imagine that we're going to nail one of our sodium street lamps to the back of a space shuttle. I'm going to skip over some of the technical details here, but what I want you to appreciate is that if that spaceship blasts away from us, the light from it will be redshifted, it will have longer wavelengths, and instead of seeing orange light, we see red light. And so if we know what is the true underlying source of elements in a particular radiating body, such as a street lamp on the back of a spaceship or such as a galaxy, we can interpret by how far it's shifted in wavelength the speed that it's moving at. Here's a particular example of what was for a few years, at least in 2013, the most distant known galaxy. The amount by which its wavelength was shifted was such that the ratio of the measured wavelength compared with the emitted wavelength coming from particular elements in that galaxy had a ratio of 7.5. And that quantity is known as redshift. If you look up 7.5 on this horizontal axis and ask what that corresponds to in terms of cosmic time, it corresponds to nearly 13 billion years. So the light from that distant galaxy left it 13 billion years ago, when the universe was much, much younger. We say the look-back time to that galaxy is 13 million years. So actually, because of the Doppler effect, it's really pretty easy to measure the speed at which a galaxy is moving towards us, in some cases, or moving away from us. Vesto Slipher and later Edwin Hubble made important pioneering observations relating to this, and specifically putting together the speed at which a galaxy was receding from us and the distance that a galaxy is from us. And they found an amazing proportionality. Close objects, things tended to move away. Further away objects moved away much faster. It was a complete proportionality. The further away a galaxy is from us, the faster it is receding from us. This relatively simply expressed observation reveals a profound truth about the nature of the universe, which is that the universe appears to be expanding. Now just imagine that we've got 3 galaxies here lined up at a particular early time. The yellow galaxy and the blue galaxy and the green galaxy are separated from one another by some distance. Imagine they each separate from their nearest neighbour by a certain speed. The speed of the 2 outermost galaxies separating from one another is twice the speed at which the nearest neighbours separate. You can see that in the top row here, the separation of green and yellow is twice the separation of what yellow and blue have separated from one another. This arises because the gaps between the galaxies are expanding. Let's just explore what it means to say that the universe is expanding. Does it mean everything is expanding? No, it does not. If you are expanding, I put it to you very respectfully that you may be eating too much pudding. Is the solar system expanding? No. Gravity is governing the bonds, the orbits between the planets around the star, giving us our solar system, just as the chemical bonds in your body, the molecules that comprise your body, are holding you together. So gravity absolutely still works and is still relevant to nearby interacting galaxies. But beyond these effects, galaxies are expanding one from another because we have verified this because we can easily measure the speed of other galaxies relative to us. And this is now very well established in not quite a century, but getting on for that duration of time in which such measurements have been made. The principal point of these observations is that the further a galaxy is away from us, the faster it is receding from us. The gaps in between the galaxies are expanding. Space-time itself is expanding. Regions that are behaving according to different physics, such as chemical bonds, such as gravity, that's exactly behaving in the way that you thought it was prior to coming into the lecture theatre this morning. Very local galaxies are moving towards us, towards one another, if they're sufficiently close that their gravitational attraction overcomes the expansion of the universe, which, by the way, is often known by the term Hubble flow. Let me give you an example of what happens when very local galaxies are moving towards one another. So this is a simulation. Simulations, by the way, performed on computers, calculate numerically on the basis of the physics that we understand and on the basis of our input assumptions and axioms what something will look like. So simulations transcend the very limited window that humans have on the cosmos by indicating the past and the present and the future of particular phenomena in the cosmos, in this case, the interaction of galaxies. I'm sure you saw during the duration of that, we went through a stage of beautiful barred spiral galaxies, almost resembling one of the galaxies that we saw in the earlier image from the Fornax cluster. But outside of local effects like this, we are left with what is now known as the Hubble-Lemaître law, named after Edwin Hubble, who, by the way, read law at Queen's College in Oxford, and Georges Lemaître, the Belgian theologian and astrophysicist, cosmologist. If we have space separated, if we have space expanding and galaxies separating from one another, could that mean, if we go to sufficiently large distances, that we could have things travelling at speeds faster than the speed of light? Careful. It doesn't. It's important to realise that it is the space between galaxies that is expanding. It is not the galaxies themselves travelling with respect to their local medium at whatever fast speed you want to think about. The rate of change of distance of a galaxy over here compared with a galaxy over here could precisely exceed 300,000 kilometres per second, the value of the speed of light. But that doesn't mean to say that something is travelling with respect to its local medium at the speed of light. It's also worth saying that if there's a galaxy moving at the speed of light away from planet Earth at a speed such that the distance between it and us is faster than the speed of light, light from it will never reach us because it would need to travel faster than the speed of light to do so, and that doesn't happen in this universe. So let's think further about what it means, the fact that everything is flying apart. Let's think about time in reverse. If things are flying apart now and expanding, at earlier times they were closer together. And at the start of this leads us towards something I'm now going to describe, which is the hot Big Bang. I didn't think the word frozen should be left alone in this particular discussion. So now I want to move on to what we can learn about the hot Big Bang. So we discussed the fact that the sky is dark at night, and that's already a bit of a clue about the fact the universe is expanding and stars have finite lifetimes. But let's not be parochial and only think about the electromagnetic radiation or the light which can be seen by our human eyes. Thinking beyond that to the rest of the spectrum, to radio light, to infrared light, to X-rays, to gamma rays, again, bearing in mind what I said in my last lecture, that the only difference between light from the left-hand side of this plot versus light from the right-hand side of this plot is wavelength. If we look at the sky at different wavelengths, specifically a wavelength of about 1 millimetre, then we see a different picture. So I'm now going to show you an image of what the entire sky looks like, taken from a satellite called WMAP, receiving electromagnetic radiation or light with a wavelength of just 1 millimetre. First of all, let me explain the plot that I'm showing. This oval shape, this elliptical shape, is actually a projection, a representation of the entire 4 pi of sky, but spread out into 2 dimensions so that it goes onto the screen. So much like a map of the globe might be shown with a Mercator projection or a Peterson projection, this is a projection of the entire sky in what are known as galactic coordinates. That's galactic with a capital G, denoting that we're talking about our galaxy, the Milky Way. And in fact, this great big red splodge all the way across the middle of that is the plane of our galaxy. It's a bit saturated out because it's bright, but if you model that very carefully and subtract it out, then this is a better image of what the background radiation looks like at a wavelength of about 1 millimetre. This is the cosmic microwave background radiation. There are many remarkable things about this, one of which is that this light left its emitters when the universe was hugely younger than it is now, specifically at an age of about a few 100,000 years. It was discovered by 2 chaps at Princeton called Penzias and Wilson. This is a picture of them here, looking a little bit moody, given they discovered something really quite exciting, the cosmic microwave background. What's important about this? It's important and remarkable that it's out there, that it exists, that despite the sort of blue-red shading of my previous plot, it's actually very, very extremely similar in all directions. It was discovered in the 1960s, and it has a remarkable spectrum which tells us that throughout the entire sky, there was a hugely uniform thermal history to the universe. The different bits of the sky that I showed in that image were never in causal contact. No way. Therefore, because the universe has this very, very similar spectrum, very, very similar intensity, whichever way you look, it tells you that the universe was doing the same thing everywhere at the time that the plasma which gives rise to the cosmic microwave background radiation was evolving and changing. Specifically, the cosmic microwave background radiation forms when, at a very important epoch in cosmic history, which is when matter and radiation decoupled from one another. Prior to this epoch, matter and radiation scattered off one another, and that's why, I said earlier, at early times, the universe was opaque to light. It's because the universe was so hot and so dense that photons, i.e. light, scattered off the protons and electrons and neutrons and a few other bits and pieces that were moseying around at that time. Now, the universe was expanding. I've indicated why we believe that's the case for the most recent 13 billion years in the universe's history. We also believe it to be the case at earlier times still. But when you've got a universe that's expanding, when things can cool and lose energy, which always happens when you expand, you begin to be able to form things like atoms. Many of you may know that the hydrogen atom, our simplest atom, is composed of a proton and an electron. Now, those two bodies won't form the single entity of a hydrogen atom if it's too hot, because there's no way that the electrostatic charges can overcome thermal energies if those thermal energies are too hot. They'll just be whizzing around and in no sense one coupled atomic entity. But that's what happened at the moment that the cosmic microwave background was formed. And that's why it's sometimes referred to as the surface of last scattering. It's the last time in cosmic history that all the radiation, all the light that was being emitted from all the energetic particles in the plasma soup at the time were scattering off one another. You can see different colours here, red and yellow and green and light blue and dark blue, and they do indicate slight variations in the intensity and in the spectrum, and specifically the temperature of the cosmic microwave background. They're amplified up to bring out the differences. But actually, this is perhaps misrepresenting a fundamental characteristic of the cosmic microwave background, which is that it's amazingly uniform, amazingly smooth, amazingly similar in all directions. The cosmic microwave background is actually smooth to 1 part in 100,000. And that's very smooth indeed. If you were about to dive into a swimming pool and the surface of that swimming pool was similarly smooth, then the largest ripples you could have on that swimming pool would only be 1/100th of a millimetre high. But actually, let's put this together with the fact that the cosmic microwave background is fundamentally very, very smooth indeed. Let's put that in the past, let's put that together with the universe in more recent times. What word would you use to describe that? You wouldn't use the word smooth, you wouldn't use the word uniform, you'd use the word lumpy. The universe is lumpy with these discrete galaxies. So how on earth in cosmic history do we get from this remarkably smooth and uniform cosmic microwave background radiation, which we can observe by looking back in time, almost all the way back to the beginning of time, but then coming back a few 100,000 years, to the galaxies that we see in the subsequent 13 or so billion years of the most recent cosmic history? Well, gravity is our friend again. If you imagine that hot cosmic plasma just turbling around, and some regions are slightly hotter and more dense, and some regions are slightly cooler and slightly less dense, and you think about what happens when you've got a slightly overdense region and a slightly underdense region. Gravity works in the direction of attracting matter. So if you've got a slight inhomogeneity, a slight variation in the local density, if you've got a slightly dense bit, what's going to happen? Slightly dense is going to become a bit more dense. A bit more dense is going to become jolly dense. Jolly dense is going to become very dense. And once gravity is at work, that enables the formation of galaxies. So overdensities of matter that existed from the earliest times subsequently collapse under gravity to give us galaxies. There's quite a long process, and a process that is not fully explored and understood, but is the subject of very active investigation via observation, via theory, via simulation, to understand the processes by which galaxies form. But the earliest coagulates, condensations of matter, are the proto-galaxies of the future universe. Within the proto-galaxies, where you've got matter that becomes sufficiently dense, you get proto-stars. Gravity continues to operate and attract matter to itself. And as the densities increase, the temperatures increase. Once your temperatures are sufficiently high, then a very important process in the universe can occur. This process is nuclear fusion. What do I mean by nuclear fusion? That's the process whereby what we call the nuclei, the protons or the neutrons or the coagulates of protons and neutrons that make the inner bits of atoms, if they are at sufficiently high temperatures, that they've got sufficiently high temperatures that they can overcome the repelling electrostatic forces, then they can fuse together to become more massive nuclei and become heavier elements. This is the process by which stars burn or shine. Nuclear fusion is essential to the universe appearing the way it does today. Stars can't shine without this fundamental process of fusion taking place. Fusion releases radiation, and that is starlight. Within stars that are undergoing the process of nuclear fusion, as nuclei fuse together, starting with, for example, primordial hydrogen or primordial helium, then heavier elements, so-called, can be made. What do I mean by heavier elements? I mean things like carbon and nitrogen and oxygen, things that are crucial for the building blocks of life. Those are made in stars. They are not made at the earliest times. We do make, as I'll describe in a moment, much lighter elements like helium, like lithium. But these heavier elements, carbon and nitrogen and oxygen, all the way up to iron, those are made in the normal everyday business of being a star and evolving in the way that stars do. So where do those lighter elements come from? Where do helium and lithium and beryllium come from? Well, let's go further back in time. 1 second after time began, time beginning at the Big Bang in the paradigm that is widely accepted throughout the community, 1 second after this, all that existed in the universe was radiation and the most basic constituents of matter, protons and electrons, and a few other energetic particles like neutrinos. And it was possible for some of these to form into neutrons, which some of you may know are part of the nuclei of many atoms. But at these very early times, 1 second after the Big Bang, it was sufficiently hot that there was no way that you could have an electron and a proton orbiting round another, being a hydrogen atom that lived happily ever after. No way. All of these particles, that electron and that proton, had way too much energy to stick together. It was one big plasma soup. But you did have lots of various different particle reactions going on, forming neutrons, forming neutrinos, that were undergoing in the first few minutes, at a time when we believe the universe was expanding. With expansion, inevitably comes cooling. And so you do start to freeze in the relative ratios of the electrons and the neutrons and the protons and the little entities of, say, a couple of neutrons and a couple of protons, which, by the way, forms the inside of a helium atom. And so it was at the earliest times that we did get predominantly hydrogen, but also a bit of helium, bit of lithium, bit of beryllium, all the so-called light elements at the top of the periodic table. But as is evinced by the fact that lots of bodies are here in the lecture theatre, there is clearly more to life than just hydrogen. A 70-kilogram human being, if they eat a nourishing, balanced diet and eat all their greens and get all their trace elements, should comprise at least the following elements and more. So where do some of the more obscure elements come from? If it's not from the first few minutes of the following the Big Bang, first few minutes of cosmic history, and if it's not in the insides of stars during normal stellar evolution processes, how is it that we have a periodic table, thanks to Dmitry Mendeleev, of all the different elements? Where do they all come from? Well, it turns out that, as I indicated, we get neutrons and protons in the first few minutes that form those very light elements at the top. And I should mention, by the way, that the observed so-called primordial abundances of the different light elements, hydrogen relative to helium, relative to lithium, if we look back at some of the oldest stars in the universe and ask the question, how much of those different elements do they have relative to one another? And we compare that with theoretical modelling for what particles we expect at the earliest times, they are in exquisite agreement with one another. This does not constitute proof, it constitutes strong evidence which gives us confidence that the Big Bang model is about right. Here is an image. This arrow points towards the oldest star that we know of at present in the universe. It's actually only about 6,000 light years away from us, but it is well over 13 billion years old. And if you look at a spectrum of that star and ask the question which chemical elements are present and understand about the evolution of the star itself, the fusion that's gone place inside that star thus far, you come up with relative ratios of hydrogen and helium and lithium and beryllium that reflect what is calculated for the first few minutes. The heavier elements in the bottom of that periodic table, where do they come from? They're more exotic, of course. They actually come from more exotic phenomena in the universe, such as supernova explosions, when a massive star explodes, or the explosion of a nova, when so much matter gets loaded onto the surface of a compact object, like a white dwarf star, that thermonuclear runaway situations happen, and all sorts of unusual fusion processes can occur and give rise to some of those more extreme elements at the bottom of the periodic table. I realise I've covered quite a lot of ground and quite a lot of cosmic history in the past hour, but I want to summarise by emphasising the 4 tenets on which our current understanding of the evolution of the universe, starting with the hot Big Bang, is based. There is the observation, which has been widely reinforced by observers all over the world throughout the last several decades, that space-time appears to be expanding. Galaxies, as long as they're sufficiently distant from us, they're racing away from us more rapidly if they are more distant. The very existence of the cosmic microwave background points to a very hot, very uniform experience for all of the universe at early times. The relative abundances of the light elements, helium and lithium and hydrogen and beryllium and boron, those relative abundances appear to be consistent with calculations for the thermal evolution of the very early universe as it was expanding. And finally, the anisotropies, the variations in different directions of the cosmic microwave background, they give us a bit of a clue about the subsequent seeds of structure formation, the formation under gravitational collapse of protogalaxies into the beautiful galaxies that we see today. All of these 4 things are encoded in the electromagnetic radiation that we receive here on Earth. They are frozen into the signals that we pick up here on Earth. That information is truly frozen in time. Thank you.